Right, so we're recording. Okay. Oh, let me fix my tents real fast. Okay. All right, so let's look at what are we doing next few weeks, and then today, and then here, this week. Okay, so next few days, I want to finish simple harmonic motion and waves. And I want to get started on electricity by the end of this week, so Thursday, Friday, get started on that. Okay. Electricity is going to take us at least a week. Now, April 16th is probably a bit optimistic. It's probably going to take a few days more than that, but sometime mid-April, we'll have actually finished everything, all topics in this class. So we'll have a good, at least a week, maybe two of review. Okay? And then your guys' AP exam is exactly 1 month from now. Yeah, so right around the corner. Okay? So you guys will be pretty ready for that. Okay? Oh, you guys may have noticed, in addition to the extra multiple choice modules that I threw up on AP Classroom, like if you want some extra study material, there's a bunch of extra multiple choice questions up there. Over the last weekend, I also put a bunch of FRQs up there, which we may not get to in class, but if we don't, then if you want some extra to study, then those are up there. Right, so this week, what's going on? A lot of you guys just turned in your chapter 13 homework, so give you guys credit for that. Okay. Our main focus today is going to be Speed of Sound Lab. Now the page that goes along with that looks like this. So you guys at home want to have that, and everybody in class, you guys got this out? Okay. I did print out a few extra copies in case anybody lost it. So I'll ask you guys in a minute if anybody has lost this. Okay. Also, I gave you guys a new page. So simple harmonic motion and waves quiz looks like this. When you guys walked into class, this should have been on your desk. Did anybody not get this page? Anybody not get this page? Oh, okay. So everybody's got one, it looks like. Okay. And then you guys at home, I just posted this to Google Classroom this morning. Okay, so this is up there. Okay, so this will be an open notes take-home quiz, just like most of them. And I'll pick that up Friday. Okay, so do Friday. Okay. Or if you want to turn it in early, that's fine too. Okay. Remember, tomorrow we're going to go over the Unit 10 multiple choice questions. So have those finished by then. A lot of you guys have already finished those early, right? Just like your chapter 13 homework. Some of you guys turned in that last week too. So if you finish that early, then awesome. But if you haven't, then just make sure you do it before tomorrow. That's our main focus tomorrow. Okay. Wednesday, I want to take Wednesday and do as many FRQs as I can with you guys. So between Unit 6 and Unit 10, remember Unit 6 is simple harmonic motion, Unit 10 is waves, but yeah, there's a good amount of crossover. Right, we'll do as much as we can with that. Right. Then Thursday, start electricity, and of course Friday, if you haven't turned in by then I will pick up your guys' quiz, which is on your desk right now. Okay. You guys got any questions? Good. All right. So, does anybody need an extra copy of this lab? Okay. So this lab involves standing waves. So I want to give you guys a review of standing waves, right, what this is about. Okay. Now the rules for setting up standing waves are different for different setups. Okay. You can have a standing wave on a string. Let me present my screen for just a moment here. Present screen, to share, about this. See, where is, no, that's not what I'm looking for. There's standing waves. Okay. Okay. No, a wave does not have to be a standing wave, but today we're going to be working with standing waves, so get to review these. Okay. Now, what you're looking at is an animation involving standing waves, maybe on a string, something like that, okay, which is not quite what we're going to be doing, but it's a good place to start. Okay. So how many, or do you guys see with that snapshot right there, there's, you guys see one node in the middle, and actually a couple other nodes too at the endpoints. Okay. You guys see two antinodes antinode here, antinode here. Okay? And how many wavelengths do you see right there? Yeah, one, exactly one, right? Scroll back a bit. There was, yeah, that's half a wavelength. Then it goes to 1, then 1.5, then 2, and then there's a pattern that you just set up. It looks like some multiple of half wavelengths at a time, like that. Okay? Now that's for a string. Okay? What about for pipes? Oh, also that was a transverse wave, wasn't it? Like transverse. Right? We're going to be looking at sound waves, which are longitudinal. Okay? So some do with maybe like setting up stand waves in pipes, something like that. Okay? We draw a bunch of pipes. Think about what kind of stand waves you could set up in different pipes. Okay? Some musical instruments are pipe-based, right? Like flutes and recorders, like trumpets. Got some kind of pipe going on. No, I might have a pipe that's open at both ends. I might have a pipe that's open at one end and closed at one end. Right, those are the most common setups. I guess you could have a pipe that's closed at both ends. Maybe if you're inside of like a closed room, there's like a stand wave setup, something like that. But most commonly, you'll see one of these two scenarios are either open at both ends or closed at one end. Right? Maybe I have some air that's blowing through this. Right? Now, the longest wavelength that could be set up, which would correspond to what's called the fundamental frequency, would be a situation where you have like a high pressure point in the middle, and then the like low pressure points near the ends. So if I try to draw that, try to represent that with a bunch of dots as air molecules, it might look something kind of like that. Okay? Now that was really hard to draw and hard to interpret. So it's really common to, even though this is, sound is actually a longitudinal wave, to represent it in transverse form. So something like this, right? Then cross it over on itself, just make it more obvious. Okay? Right. So if it wasn't obvious before, you guys see like a node here and a couple of antinodes, right? Right. So whenever I draw a transverse wave for this lab, it really represents a longitudinal wave that has where the nodes represent high pressure points and the antinodes represent low pressure points. Right? You guys got it? Right. Now, how many wavelengths do you see here? Half. Good, because like from this trough to this crest, that's half the story. Right? And then to complete the full wave, I would need like another half one. Right? So the length of this pipe is half of the wavelength that's being set up there. Right? Now that's not the only wave that will resonate. Maybe I've got a stream of air going through this like that. Right? There's another set that will also resonate. It could look something kind of like this, where of course got high pressure point here, high pressure point here. So now it's like there are two high pressure points, kind of like that. Okay. So still linked to the pipe. How many wavelengths do you see right there? One. Yeah, like crest to crest. That's one wave, or trough to trough. That's one way of measuring wavelength. Okay. And then the next possibility, probably do something pretty close to this. Nope. Is that right? Yeah, no, that's fine. How many wavelengths do you guys see right there? Yeah, 1.5, right? So crest to crest would be 1, to trough is a half. Yeah, so the length of this pipe is like 1.5 wavelengths, like that. Okay. Right, so those could all be standing waves that could be set up in that kind of pipe. Okay. What if we close one end of the pipe, which is going to be close to what we're doing today with this lab? Okay. So the rule here is that you have a high pressure point on the closed end, and then a low pressure point on the open end. So it might look something kind of like that. Okay? Or maybe you're maybe like blowing into a glass bottle, right? And then it's up a standing wave, just something like that, right? Okay. How many wavelengths do you guys see right there? A quarter. Good call. So the length of this pipe would be a quarter of the story for the wavelength. Okay? Now, what's the next opportunity that could set up a standing wave? Well, you guys see what the physical rule is, right? High pressure point here, low pressure point here. So the next opportunity for that to happen would look something kind of like this, wouldn't it? Okay. How many wavelengths is that? Yeah, 3/4. So the length of this pipe is 3/4 of wavelength. Okay. See, it's not quite one full wavelength, right? You need like one full S shape, so it's a little bit missing there. Okay. And then the next opportunity to set up a standing wave might look something kind of like this. Okay. How many wavelengths is that? 5 quarters. Good call. 5 quarters. Okay. So, ooh, I see a pattern set up. About 1/4, 3/4, 5 quarters. Hey, is it increasing by half wavelength at a time? Here. Hello, Mr. Griffin. Yeah, sure. Lisa, looking for you at the office. Okay. All right. And okay, so the last thing you mentioned was that it looks like it's increasing by half wavelength at a time. Of course, the length of the pipe itself is staying the same. Right? But that was the same story actually with the yeah, same story over here. Is also increasing by half wavelength at a time, which was also the story for the string, like setting up stand waves on a string. Right? But they started at different places. Actually, the pipe open at both ends is a really similar story to the string. Right? The pipe closed at one end starts on a quarter, right? Quarter, 3/4, 5/4. Now, last class, somebody was asking me, is there like a formula that goes with this? Yes, there are formulas. Let me point it out in the book real fast. See, chapter 14 in your book is sound. Okay, so here's some pretty good looking formulas, right? So this would be for pipes. Let me see if I can find it for strings. Okay, so here's strings. Okay, they talk about strings going on, right? And here's the formulas for setting up standing waves on strings. So the fundamental frequency, 1 divided by 2 times the length of the string, and the square root of, I have F divided by mu. What do you guys think F stands for in this context? Capital F. Force. Yeah. What kind of force specifically on a string? Tension. Yeah. That would be tension in a string, wouldn't it? Okay. And then mu. That's a more obscure one. We've talked about this, I think, once before. Like, what property of the string? Mass per unit length. Yeah, mass per unit length, right? It's called linear density, right? Okay, so if AP wanted you to do something like that, they'd have to give you the formula. Like, you wouldn't be expected to memorize that. Okay. Then right, setting up in pipes. Hey, look, this looks a lot like what I was just drawing, doesn't it? Right? Then what are the frequencies that can be set up? Okay. So here we've got n times v over 2l, right, which should be n times the fundamental frequency, where n is just some whole number, right? 1, 2, 3, so on. Okay. Let's see, natural number. Right? And then that's for pipe that's open at both ends, right? Something like that. Right? Now, pipe that's closed at one end, it follows this. We got n times v over 4l, so or n times the fundamental frequency. But the catch is here, if you use this particular format, you can only use odd numbers, so 1, 3, and 5. Okay? Some textbooks will write that formula a little bit differently, but anyway, that's your textbook's perspective. Okay. Okay, so let's go to this page. Okay. Now here's the setup. Right, so the goal is to find the speed of sound. We're going to calculate the speed of sound in class today, and we're going to do that with just with tuning forks and PVC pipe and meter stick. So I've got this whole box of tuning forks. Look like these. Right? There's a place for a hammer. Strike these things. Okay. I pulled some of these out for last class. The shortest ones work really well for this particular lab. All right, so here's the 3 shortest ones. Should be the highest frequencies, wouldn't they? Okay. And these have numbers stamped into them. Like this one says 480 and has a letter B. Guys, what do you guys think the 480 means? Yeah, frequency in hertz, right? Now, there's a weird thing about these. Remember I was telling you guys the other day that an A note is defined as 440 hertz? Okay. Now, that's a standard, but this particular set of tuning forks, kind of side up here. Oh, do I have the A note? Yeah, here's the A note. They've actually down-tuned it a little bit. I don't know why. I don't know if it's just like some other popular standard maybe or something, that they've tuned the A to 426.6, but the other ones are consistent based on that. So, okay, I guess. Okay, so anyway, that's what we're working with. Okay, now, how are we going to use this to measure the speed of sound, or to calculate the speed of sound, I should say? Okay, so look at this this diagram. Or what I'm going to be doing is putting a PVC. I'll turn the camera here in a moment so you guys can see the actual experimental setup. But we're going to there's a beaker of water, like a lemonade pitcher, full of water. Got a PVC pipe. I'm going to put that PVC pipe down in the water, and the length of the PVC pipe, of course, is going to be the length of the pipe, except that it's going to stop where the water level stops. Right? And that sound wave is going to bounce off the top of the water. So when I push the PVC pipe down to the water, it effectively makes the pipe shorter, doesn't it? The effective length would be shorter. And at some point, there's going to be like some shortest level where it resonates. It's going to set up a standing wave, and you'll be able to hear it. Right? So as I move the pipe and then the tuning fork above it up and down, so like, it's going to resonate at some point. Right? Now, the shortest place that happens, you might say, well, couldn't I just take that? That would be a quarter of the wavelength, multiply that by 4, get the full wavelength, and then, oh, hey, if I know the wavelength and I know the frequency because that's stamped onto the tuning fork, hey, I could put 2 and 2 together and get the speed, couldn't I? Okay. Well, or you might say that there's a few more boxes to go on here. So we're actually going to use a slightly extended procedure. There's sort of a catch with this, which is that what I told you about, go back to this, right? About here, like especially these 2 pictures. You guys see these 2 pictures we're going to be basically using? Right? Well, what I drew there is not exactly true. Right? The true like quarter of a wavelength actually extends a little bit beyond the pipe, and same thing for 3/4, actually extends a little bit beyond. Right? Now, what is a little bit beyond? Well, that has to do with like the diameter of the pipe. There's like a formula you can feed it into, but we're not going to do that. What we're going to do is we're going to take the difference between these two, between this and this, right? Between the now the I should say this too, is that this pipe will be approximately 3 times longer than this pipe, so the wavelengths themselves will be the same length for any particular musical note. Right? But by taking the difference, then whatever that difference is, where the wave extends a little bit beyond the pipe, that will also be subtracted out, right? Which means that the difference between these two would represent half wavelength. Okay, you guys hear that? Okay. So then, go back to here. Okay. Once we got those 2 places where it resonates, and here's the second picture, the L2 where it resonates, right? That difference would represent half of a wavelength, right? 3/4 minus 1/4. Right? Remember, L2 should be approximately 3 times L1, but maybe not exactly. Right? Then, once we have that difference, which is half wavelength, well, if you just double that, hey, look at this. Wavelength is equal to 2 times that difference. That should make sense too, shouldn't it? And then once we got the wavelength and we got the frequency, because that was stamped into the tuning fork, multiply that together and we'll look at the speed. Okay, you guys okay with that premise? Okay. Few things I want to show you guys before I get around with this. Show you guys a short Paul Hewitt video on resonance with tuning forks. Here it is.
Hi gang, sound time. If this room were filled with ping pong balls and I had a big pedal and I shook it back and forth, I'd send vibrations through this ping pong balls. Same kind of thing happens when I strike this tuning fork. This vibrates back and forth. It's the air. You get vibrations. That's what you pick up the sound. Here I have a fork, frequency, same. Watch, listen. Strike this one. This one vibrates. 4. As long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. Huh? What happens if this fork has a different frequency? Let's try now. Yup, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with the radio set. The radio signals are coming in, and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
All right, I'm getting a question in Google Chat. Let me know about that. So looks like a couple of you guys are having trouble finding the speed of sound page, lab page.
Yeah, Mr. Griffin.
Yeah.
I don't think it got posted. I think because it's not under the assignments.
Huh. I'm looking for it. Why did it not get there? Nobody mentioned this last class. Huh. Oh, it really isn't there, is it? Wow, okay. Yeah, let me post that real fast. Take a minute here. Let's find this. What happened? Okay, labs. Beta Sound Lab. Okay. Create. No. So, I wonder if maybe I just posted this to one class or something. Alright. 3, 4 on my blocks. Okay, this is for topic, oscillation waves. Okay, so, okay, so it just posted now, so it should be up there. Yeah, sorry about that, guys. Okay, so you guys should see it now. Okay. All right. Oh, remember the other thing I wanted to mention about this is I want to test these because yeah, these tuning forks do have numbers stamped into them, but a more scientific thing to do would be to actually test these with a tuner. Say, does the tuner actually agree with the frequencies? Okay. Now this is kind of hard to do. Let me take the biggest fork that we have. Okay, so you guys see the biggest fork. It says 256 C. So 256 should refer to 256 hertz. Okay. Let's see if we get that with the tuner. It's having trouble picking it up at all. Okay. So here. Oh, like down here. Oh, hey, that was a good idea. Hey, look at that. Huh. Yeah, so it was reading 256, and then it kind of drifts down to 253. Okay. Yeah, you guys see that? Okay. But yeah, okay, so that's a pretty good. Let me try some of these higher ones. I was having trouble with these higher ones earlier, but let's see if we can get this work. Huh. I think it's picking up some of these overtones, so it's like multiples of the number. At one point, it was flashing like 400 and something up there, and this says 426.6. So yeah, yeah. Do you have a question?
Yeah. Do you think it might be dropping the frequency because of music, or does that make a difference?
Well, the frequency would refer to like a musical note, right? So it might be picking up some of the overtones.
Well, I'm talking about when it just goes down like 3 hertz, like
Huh.
with the other one, where it went from like 426 to like 423.
Like, why does it go down?
Yeah, I'm just wondering if it's like because it's damping like this.
I don't know why the frequency is going down. Like going down would refer to like a lower pitch, like getting quieter has to do with the decrease in amplitude, which is a different idea. So yeah, I don't know. All right, but try this out. All right, so turn my camera. Mode here. Workstation. All right, so I got 3 tuning forks signed up. I picked the smallest one. Yeah, right, so the smallest one right here. Okay. See if you guys can hear where it resonates. Right, so you guys see my setup, right? I've got water, I've got this PVC pipe, right? And then the effective length of the PVC pipe just goes to the top of the water. Did you guys hear that in class? It's going, wow, wow, wow. Right, so we're just really loud. That's the point that I'm really interested in, because it's setting up a standing wave. So I need to measure, where's that happen? Right there, that's it. Okay. So I'm gonna go from the water level to the top of the pipe. Okay. Now is the top of the pipe the exact place where the wave stops, or the quarter of the wavelength? Not exactly, but that is built into our procedure. I'm gonna, there's two places and take a difference. So right here, this is reading at 15 centimeters. 15 centimeters. Okay, so I'm gonna go to, oh, I forgot to record the frequency. That's 512 hertz. So for 512 hertz, length one was 0.15 meters, right? So it'll be 15 centimeters. Right, so that's the first data right there. So 512 hertz, we're looking at 15 centimeters or 0.15 meters. Okay, now I need the next place where it sets up a standing wave. Okay. And the next place, it should be approximately 3 times the original. It should be approximately 45 centimeters, which would be maybe at least this tall. Okay. But probably not exactly. So let's see. Right there. You see that? Let me do that again. Like right there. Okay. I guess I was getting really loud right there. Okay. So let's say what's this distance from the water level? Looking at it's saying like 50.5. Right? It's like 50.5. Alright, so that'd be 0.505 meters. I've been trying to round to the nearest centimeter for a lot of these, but it's kind of halfway in between. Okay, so let's finish off with this. Right, so the difference between those two lengths, it is 0.505 minus 0.15. I'm looking at 0.355 meters, so 35.5 centimeters for the difference. Okay. Now the next box says to double that number, and that should represent the wavelength. Wavelength is 2 times that difference, okay? 2 times half wavelength. So times 2. Looking at a wavelength of 0.71 meters, so 71 centimeter long wavelength. Okay. And then finally, to get the speed is equal to wavelength times frequency. So I'm going to go 0.71 meters times a frequency of 512 hertz. That's telling me about 364 meters per second. There you go. Speed of sound. Okay. Guys, what number have we been using in the last week for the speed of sound? Yeah, about 343-ish, right? And of course, that depends on the temperature and the pressure, but hey, look, 343 to 364, that's not too far off. That's actually pretty close. Let me see what percentage drop that would be. Was 364 compared to 343. Ooh, it's only about 6% off. So it's actually pretty close, at least from what I expected to be. Let's try this with a couple other tuning forks. So the next one up is, let's go this guy, 480 hertz, 480. Right. This is the next smallest one. I think I mentioned the smaller tuning forks are easier for this particular lab. Yeah, let's see where it sets up a standing wave here. The first one, L1, do you think it's going to be a little bit more or a little bit less than 15 centimeters? It's a little bit lower frequency. Yeah, so the wavelength should be a little longer, right? So I bet it's gonna be a little more than 15 centimeters. Let's try. Let's see what science says about this. Right there. That is at 17, pretty much exactly, 17 centimeters. It's 17 centimeters. So be 0.17 meters. Okay. Now what's the next place that's gonna happen? Okay, so I'm guessing it's probably gonna be about 3 times that, which should be at least 50 centimeters. Yeah, okay, so I think 2 pipes stacked on top of each other should be able to handle it. Yeah. Oh, yeah, it's right there. Right about there. That one's kind of subtle, kind of hard to tell. Okay. Looking at 57 centimeters. All right, so 57 centimeters, so 0.57 meters. The difference between this, difference would just be a 0.40, wouldn't it? Right? See the difference? Okay. If you double that difference, then you should get the wavelength. Be this many meters. Right? Compare this wavelength to the old wavelength, right? I mean, this is a different tuning fork, right? Okay. Look at that, the wavelength's a little bit longer, which makes sense because it's a little bit lower note, right? Less frequency. So finally, speed is equal to wavelength times frequency. So take the 0.80 meter wavelength, multiply it by 480 hertz frequency. What is 0.8 times 480? Looking at 384 meters per second. Okay. You guys get that? So that's how that turned out. Let's assume for a moment the speed of sound is actually 343. What is 384 compared to 343? It's about 12% off. Ooh. And then last one. Okay, so the biggest tuning fork I got here is the one that says 426.6 on it. 426.6 hertz. Good at that. I heard it right there. Okay, and then this point is what's it gonna be? It looks like 19.5. Let's see that. 0.195 meters for L1. Okay. Now if I triple that, that'd be pretty close to 60 centimeters, wouldn't it? All right. So what I'm gonna do is take this paper sleeve. Okay, here. All right, push this in here. All right. Then this will let me extend this pipe. Extend a little bit longer. Okay. Is this gonna work? Awesome. Right. The 60 centimeters is kind of long. All right. So if I can get this to resonate. Try this. Yeah, I think it's right out here. Yeah, it's pretty close. Yeah, that was really subtle, but it seemed to get a little bit louder right there. All right, let's see what this is. This is at, 59. Yep, that's at 59 centimeters. So that's 0.59 meters. Take the difference, 0.59 minus 0.195. That's 0.395. Double that. I'm getting 0.79 meters for the wavelength. Then take 0.7. Ah, that's weird. Look at that. Looks like our empirical data is saying that the wavelength here is shorter than it was for the higher frequency. That doesn't really make any sense, but you know what I think happened? I think that this L2 is wrong. So this number right here, I don't think that's exactly right. Okay. Anyway, let's try this out. 0.79 meters, the wavelength times 426.6 hertz. That's the frequency. 426.6. That gives us, actually, this came out to a nice number though. 337 meters per second. Extremely close to what we've been assuming the speed of sound actually is. You guys get that? Okay. Let's see. Find out. So what is 337 compared to 343? Yeah, it's about 2% off. Probably really close. Yeah. You guys online doing all right too? Let's see what we got last class. So here are my numbers from last class. I did use the same tuning forks because they're the easiest ones to use. So, they're kind of somewhere, right? Let's throw that back. Okay. All right. So let's look at this right up on the back. I'll help you guys out with this one. Okay. So question we're trying to answer is, what is the speed of sound? What is the speed of sound? So how are we going to figure this out? Okay. So measuring tools. What were our measuring tools?
Measure.
Yeah. So you know what? I will put a tuning fork, or maybe I should really say a tuner. Like a tuner could actually be the measuring device, right? Okay. The fork itself, we had a number stamped on it, so that's how we were getting the frequency. But really scientifically, you would want to have a measuring tool like the tuner. That's to measure frequency in hertz. Okay? And then, yeah, you guys see like either a meter stick or a ruler, and that was to measure the distance in meters. Okay, so there you go. That's the two things that we were measuring. Okay? That's all the measurements that we needed to gather to eventually calculate the speed of sound. Okay? And so data gathering procedure, what do we use to gather the raw data? So I want some kind of point that tells me what the basic experimental setup was, and then a few points how I'm going to gather specifically these values. Right, so help you guys out here. I might say place a PVC pipe vertically in water. So that the water level closes one end of the pipe. Then strike a tuning fork above the open end of the pipe. Strike a tuning fork above the open end of the pipe. Right. And adjust the vertical level of the pipe. Until the sound resonates. Okay, so that's the setup. Okay. What about going about and gathering these numbers? So let me say that record the frequency of the tuning fork in hertz. You know, if you're being more scientific about it, you might say like use the tuner to measure the frequency of the tuning fork in hertz, right? But if you got the stamped number, then maybe you could say something like that. Right? Okay. So that's how you get this frequency. Okay. I've got maybe two more points I want to consider because go back to this data. Okay. So that's that number, check. Okay. There were two other raw data numbers we have. That's L1 and L2. So I want a bullet point for each one of those. You know, measure this, right? And then everything after that was calculations, right? This was our raw data right here, these first three boxes. So say record the shortest length of pipe that the sound resonates. And I'll call that L1. Okay. Then here's the last point I got here. Lift the pipe until the second place that the sound resonates. Record that distance. And that would be L2. Okay. So just to recap this while you guys are finishing up that part. For data gathering procedure, you'll want some point that basically tells your experimental setup, right? Oh, you know what a good thing would have been to do is like maybe to refer to a diagram. Maybe I shouldn't have done that, like refer to a diagram or something. Right? But there is a diagram on the front here anyway. Right? Shows exactly what's going on. Okay. Then you need to say, well, how are you going to use these measuring tools to measure just your raw data? And there were 3 points of raw data we have. Right? We've got the frequency of the tuning fork in hertz, and then there were 2 distinct places where the sound resonated. Okay. Oh yeah, Morgan.
So from longitudinally, where the tuning fork is resonating, is that a high pressure point or a low pressure point?
It'll be a low pressure point. Yeah, sure. Kind of a weird thing, but it'll be. Okay. All right, and then how to analyze this data. So what are we going to do with this raw data to eventually answer this question? What's the speed of sound? Okay. So take the difference in lengths of the 2 places where the sound resonated. Right. I'll call that delta L. So delta L equals L2 minus L1. Right. What I'm thinking too is let's say you got this exact question for one of your FRQs on the AP exam, which you could, actually, this could be a really classic question they could ask. Right? I would think that having this formula jotted down would be really important. Imagine from the point of view of an AP grader, like an AP grader probably has hundreds of these that they're going through, right? They probably got some checklists that they're grading off of, and they might see that you got frequency and hertz check, L1 check, L2 check, right? As, as they're trying to shuffle through hundreds of papers, right? And then, oh, hey, look, a nice formula right there. So, I mean, this sentence explains the formula, but this formula stands out. It's a lot easier. It's a lot more obvious to see, right? So make sure you got that. Okay? Then what did we do after that? Think about what we did. Why did we take the difference? We took the difference because that represents a proportion of the wavelength that specifically represented half the wavelength. So what did we do with that number? Well, we doubled it so that we could get the full wavelength. Right? So that eventually we could use that to get the speed of sound. So let's say double that difference. Double that difference to get the wavelength. Or maybe I should say to calculate the wavelength. To calculate the wavelength. Okay. And then the wavelength then would be 2 times the difference in length. Okay. Or if you like, maybe you could say this wavelength equals 2 times L2 minus L1. Okay. Some version, like one of those. And here's the last thing that we actually did was we said, well, speed is equal to wavelength times frequency. We now have the wavelength. We had the frequency to start with. So multiply wavelength times frequency. To calculate the speed of sound. Right. That's going to go, of course, speed is equal to wavelength times frequency. Okay. Of course, you guys know too that almost certainly one of the, yeah, Trey? Yeah, how to analyze data, right? So remember the difference in thought process of these, right? So anything that has to do with data gathering is if you're gathering the like the direct raw data, and anything to do with data analysis, now you're taking that raw data and you're plugging it into equations to solve for things. Like for example, this wavelength was not a direct measurement, but it came out of saying, well, it's 2 times this difference, so it was like a calculation. Yeah, there you go. Yeah. Now you guys know too that like almost for certain, you're going to get a point by saying like take multiple measurements, right? Like repeat measurements. Okay. So do something like that. So I'm going to say repeat measurements and use different tuning forks. Oh yeah, actually you're probably right. Yeah. So yeah, good point. So repeat measurements actually probably fit better up in this last section. Okay. Reason I'm thinking down here is because I'm gonna say take an average. Take an average to determine speed of sound. Okay. Yeah, so multiple measurements is good for data gathering, and then take an average is good for analysis. Okay. Let's see what the average of these speeds would have been. It was 364, 384, 337. Right. Divided by 3. Right. So the average I'm getting, maybe I'll put that in right here. So we got B sound average equals, you guys know whenever you put a bar, just a flat bar above a variable, that could refer to like an average value. Right? So I'm doing 364 meters per second plus 384 meters per second plus 337 meters per second. Right? Divide by 3. Right? And that's telling me 362 meters per second. So that's the answer. Speed of sound is about 362 meters per second. You guys good? You guys got that? All right, so, oh man, didn't realize it done. Okay. For video recording, everything we just did was a very tiny screen, but yeah, guess you guys can figure out what's going on, right? All right, so you guys got your phones out? You guys got phones? All right. So let's finish off today with just a few other things just about waves. So I'm gonna present my screen, do share. All right, let's do a Kahoot on sound. Oh, where it happened here. Okay, play, teach. And then after this, we'll look at a few Doppler problems. Yeah. Okay. Now, while you guys are logging in here, remember turn in your lab before you walk out the door today. Right? Also, you guys' chapter 13 homework. Now, chapter 13 homework, a lot of you guys turned in at the beginning of class. Some of you guys turned it in last week. Right? So if you haven't yet, then turn that into the grade trade before you leave today, or upload to Focus if you're online. Right. Then I will get you guys points for that. And then remember, your guys' take-home quiz on this is due Friday.
Oh, yeah, I mean, this is half, like,
All right, so if you're hopping in a minute late, then that pin, 7-digit pin, should be at the bottom of the screen. Okay. All these, I'm a new place. All these questions are related to sound. All right, and here we go for sound. Yeah, so you guys know speed of sound, well, we just measured it. It's like 300 and something meters per second. Right? So, or I should say we just calculated it. So it's like 3 times 10 to the 2 versus speed of light. You guys know it's 3 times 10 to the 8. Ooh, isn't that off by an order of magnitude? It's like 10 to the 6. You subtract those powers. Subtract this out 1,000,000 times. There you go. Got Timbo and the lead, followed by Hyper, Alex, Natasha, and Bella. Soundwave. Yeah, it's a longitudinal wave. Okay? It's also called a pressure wave. Okay? So the air molecules will travel in the same direction as the energy that's propagating. One of the questions that you guys got on your multiple choice for AP was, what's a good model for thinking about how these air molecules actually move? Right? And there was a question about, would it be elastic or inelastic collision? Do you guys remember that question if you did it over the weekend? Right? Which makes more sense? Would it be inelastic where things kind of collide and then just stick together? Or would it be elastic where they bounce off each other, kind of like Newton's cradle? Yeah, that would make a lot more sense, right? So I hope you guys picked that one, but yeah, we'll find out tomorrow. I think you guys got that right. Pretty close to that, right? Okay. No, not exactly, because eventually the sound peters out, but probably pretty close. Yeah. Yeah, you guys got that. You guys ever heard you scream in space, no one can hear you? Okay, so sound needs a medium. Sound cannot travel through vacuum. Can any wave travel through a vacuum? Yeah, light. Yeah, otherwise planet Earth would be quite dark. Yeah, so light can travel through a vacuum. Electromagnetism can travel through a vacuum, but not sound. Sound is a pressure wave, needs a medium. Ooh, sound travels faster. So you just interpret that equation right there, right? Oh, so if it were 0 degrees outside, 0 degrees Celsius, now that'd be freezing, right? So it's a little bit colder than it ever really gets in Florida. Okay. Then sound would travel at 331 meters per second. It looks like every degree above that travels a little faster, a little faster. Okay. Okay. Now, when I first saw this question, I hypothesized it would have been the other way around because I know, well, sound does travel a little faster through solids than liquids, and faster through liquids than gases. So I would have guessed cold, but based on that equation actually says the opposite. Okay. So there you go. Why is that? I don't know, but yeah. Yeah, Tibo, Hyper, got Alex on fire, Alyssa, and Elisa. Top 5. Noise canceling earphones. Your example of destructive interference. Right? You guys remember you interfere a wave with itself, and it waves exactly upside down of itself, then it will cancel out. Where does sound travel the fastest out of these options? Yeah. All right.
Pressure.
Yeah, so the general rule is sound does travel faster through solids and liquids and faster than liquids through gases. No. Why exactly is this? I don't know. I mean, I read a model that has to do with like how closely together molecules are packed. But then again, I don't know. I mean, the temperature of air kind of goes against that. So anyway, these are the empirically measured answer.
I think that like density and pressure would be almost interchangeable.
Yeah, I mean, yeah, you would think, right? But yeah, for some reason, I guess when you warm up air, which actually decrease pressure, like the opposite works. So I don't know. Got Hyper going to the top. Alicia, Jared, Moop, and Alex. Beats. Oh, all right. Yeah, so when two tuning forks have almost the same frequency and they're sounded together, you hear a beat frequency. This sort of shows for you guys. Well, I'll show you that it doesn't quite work with what we have. The two tuning forks with almost the same frequency. The closest ones I've got are maybe like 480 versus 512 hertz. Now, isn't the difference here like 32 hertz, right? Do you guys know how to calculate beat frequency? You just take the difference, right? So the difference would be 32 hertz, wouldn't it? Right? Which is probably more than our brains can perceive, but let's try it out. Just one at a time, maybe. Oh, where's the hammer? This by itself sounds like that. This by itself. All right, then what if I do the two together? Yeah. So supposedly that'd be like 32 beats per second, but I think that is just more than our brains would be able to perceive, like, like a wah, 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 where it's like 32 times per second. It did have something like that. There you go. Got more beat questions later on. So Harper's still in the lead. Jared's on fire. So you got 1608 hertz tuning fork. It sounded at the same time as piano you struck. You hear 3 beats per second. What could be the frequency of the piano string? We're trying to tune a piano. Okay, yeah, so either of these would have been good, right? So remember, the tuning fork was 1608 hertz. We heard 3 beats. Now, is it 3 less or 3 more? Well, that's ambiguous, so it could be either one of these. Okay. So 3 beats per second would sound like wow, 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 wow. Maybe that's 3 beats per second. And look, we got Hyper on fire. Unbelievable. The explosion occurs 1 kilometer away. Now, you know, speed of sound is about 340 meters per second. How much time would it take for that sound wave to reach you from 1 kilometer away? Yeah, about 3 seconds. Right? So take 1,000 meters divided by 340 meters per second. I mean, it's really close to 3 seconds. So related question coming up here. Ooh, got so Hyper, Jared, Tipo, Lisa, and Alex. Top 5. Here it is. General rule for estimating the distance in kilometers of a lightning bolt. Count the number of seconds between seeing the flash and hearing the thunder and divide by. Yeah. Okay.
Although they told us miles. It was every second.
Right. Yeah. Okay. So this answer right here is the same as the last answer. It's like 3 seconds per mile, or sorry, per kilometer. 3 seconds per kilometer, pretty close to you. That's basically the speed of sound. Okay. But Morgan, you were saying you read this in a kid's book, and they would have told you what ratio.
It was every second is a mile.
Every second is. Wait, hold on. How's it go? Sound travels.
I mean, it was a Patricia Polacco.
Okay. It's like a 5-to-1 ratio in terms of miles. So, so for example, let's say you hear, or let's say you see a flash lightning, and then you start counting. You count 15 seconds until you hear the thunder. Right, 15 seconds. How many kilometers away is that lightning? About 5, because you do 15 divided by 3, you get 5. How many miles away would it be? Yeah, 3 miles, right? So 15 divided by 5 is 3. Okay. Ooh, guys, 5 kilometers from 3 miles. Is that the same distance? Yeah, like almost exactly. I mean, slightly different, but yeah, you go. So 3 miles, 5 kilometers, pretty much the same distance. I got Hyper, Jared, Tipo, Alex, Alicia. Oh, here's something I didn't talk to you guys about. 10 decibels versus 50 decibels.
I know, logarithms.
You're onto it. Logarithms. Yep. What we're talking about. Logarithms. Okay. Yeah, so the answer is about 10,000 times. Ooh, man, a bunch of you guys got that, which is awesome because I haven't really talked about this. But the way we measure a sound, okay, we're measuring it in decibels, but this is actually, like the number of decibels that a sound is actually the exponent of some equation. I don't know the equation off the top of my head. It's in your textbook. But you do like 10 to the power of these things. And deci is a tenth of something. So it's actually 10 to the power of 10 over 10. So it's 10 to the power 1. This would be 10 to the power of 50 over 10. So it's like 10 to the power of 5. Right? So if we get 10 to the power of 5 compared to 10 to the power of 1, okay, it's off by like several decimal places. It'd be like 10,000 times the intensity. I do remember this too, is that every time you change by 3 decibels, that's like doubling the loudness. So for example, if you go from 50 to 53 decibels, that's twice as loud. 53 to 56 decibels, it's really back to like 1.995, something like that, but let's see. Yeah. Ooh, Jared, take it back to the lead. On fire. Hyper, Tipo, Lisa, Alex. All right. Okay, so if you take 340 meters per second and multiply by 5 seconds, you get pretty close to this number right here. Right? Oh, also, you guys remember that rule of thumb with the lightning, right? Every 3 seconds is a kilometer. So 5 seconds, that should be almost 2 kilometers. Hey, that's almost 2 kilometers, isn't it? Speed is equal to wavelength times frequency. Here's your speed. Here's your frequency. So what's the wavelength? Yeah, there you go. Speed equals wavelength times frequency. You need a wavelength of half a meter to make that work.
The ratio.
Ooh, bathroom, popping in the top 5. All right, there you go. So just take the difference. Okay? So 2 sounds pretty close to each other in frequency. Just take the difference. That's it. 6 hertz. So that would sound a lot like about 6 beats per second. We've got Jared, Hyper, Tipo, Alex, and bathroom. Oh, this question. You and your friend walking side by side, 79 versus 70 steps per minute. How many times per minute will you be in step?
Are you starting at the same point in time?
Yeah. See that.
Oh,
Oh, okay. Too late, wake up.
Yeah, this is actually just beat frequency, isn't it? Yeah, it's the same mathematics. Yeah. So another way to say it is like how many times per minute somebody take a photo and you'd be in like the same position, like both right foot forward, something like that. Yeah. So just take the difference.
Oh, no.
Oh, I only have 3 winners here. Right, so we have a a mystery tuning fork, but we actually know the frequency of the string. It goes kind of backwards, but whatever.
Show me.
Wait, what?
Where the show medium button. Right.
Where's that?
Under the, under the.
Oh, I never saw that. All right, thanks. Thanks for pointing that out. Yeah, so we know that the piano string itself was 1060 hertz, and we heard 2 beats per second. That means the fork was either 1058 or 1062, but it starts out ambiguous. It's one of these two guys, right? We don't know. But now the fact that we're tightening the piano string and the beat frequency goes up, that means the fork had to have been that lower number, had to have been the 1058. Okay. Yeah. So, a little tricky one there. Yep. Hyper to the top. So, take your time on that. Yeah. Speed equals wavelength times frequency. And so remember, guys, speed equals wavelength times frequency, right? So the speed should be about 340 meters per second. That'd be something you would assume. Right? That's wavelength of 0.5 meters times a frequency of 680 hertz. That would give you 340 meters per second, wouldn't it? Okay. Maybe rearrange that. Yeah. Hyper still in the lead on fire. Ooh, this one. Okay, so I got 5 winners on this one. I'm gonna try the show media trick. I played all these years teaching, I never saw that show media button. So the speed of sound in water is much faster than air. It's 1530 meters per second. It's what, about 5 times as fast? And so we're in that boat, we're bouncing the signal off the ocean floor, and it takes 12-second round trip. But we're only looking for the depth of the ocean. Right? For the depth of the ocean. So speed of sound in water is about 1530 meters per second. And going from here's our boat, and then the full round trip took 12 seconds. Time is 12 seconds. Right? Now that was down and back up. Now, different ways to set this up. One way to set this up is to say, well, guys, if the round trip was 12 seconds, then how long was the one-way trip from the floor back to the top? 6 seconds. So if I do that, if I just call this 6 seconds, then the x that I solve for would be directly the answer that I'm looking for. So I can just do distance equals speed times time. So 1530 meters per second for 6 seconds. See, 1530 times 6, that gives me 9180 meters. Okay. Another way you could have done this is you could have used the full time interval and then taken your final answer and divide by 2, because down, back up. Okay. Guys go there? Yeah, that works. Oh, Alex got it. object is forced to vibrate at its natural frequency, resonance occurs. Yeah, you guys remember the kid in the wine glass? You guys remember Tacoma Narrows Bridge? Yeah, that's called resonance, right? Yeah. Caleb Bay this morning had an interesting question I had thought of, which is, what if you got a resonant frequency over like a human being? what would happen?
I don't think we have one set frequency.
Let's try that. Yeah, but I don't know. Maybe it's person's height or their width. There might be something associated with that, or possibly be like specific organs or something. Like, I don't know. Interesting idea.
I think the most noticeable would be on the resonant frequency.
Oh. That is a good point. Vibrating loops.
Have you ever seen a marimba or vibraphone?
Seen what?
A marimba or vibraphone?
I don't think so. So what's up with that?
They're instruments, they're keyboard instruments that are based almost entirely on that concept.
What?
Yeah.
Huh. Yeah, maybe I'll Google that real fast here in a minute. Okay, so yeah, you guys know, yeah, even a steel concrete bridge had a resonant frequency that takes it out. Tacoma Narrows Bridge came in. Alex in third. Jared in second. And in first. Got Hyper. And round out the top five, got Bathroom and Timo. Okay. Hey, check us out. So you said, here goes here.
Vibraphone is the most similar to the
Vibraphone.
Yeah.
Here's a vibraphone. Pretty cool.
It has metal bars. I think they're made out of steel or silver maybe.
Yeah,
And it
interesting.
has metal resonator.
Yeah. And you said the other one was called a what?
A marimba. That one is wood though.
Oh yeah, that is what's some other thing, isn't it? Yeah.
What's the instrument that the scientist made where you put your hand in and it makes a noise and you move your hand around and it makes noises?
Oh. Yeah, that's called a what?
Last time Monica.
No, it's, I know we tried, it's a theremin?
Yes, okay.
The resonator.
Yeah, this one's, I might find a video of the theremin, because this one's a really great instrument.
The ghost in apparently tuning is a pain in the butt.
I'm sure.
Oh, you can tune this thing?
Yeah, you have to, because it changes pitch based on, like, if someone walks in the ring. Because it's pitched based on your, I don't know, I'm not sure, something with electromagnetic.
Yeah. Since you guys brought this up, how does this work? It's like one hand controls the volume and the other hand controls the pitch. Is that it? Was that invented in the Soviet Union, I think? Was it? I think it was, right? Yes. Yeah. All right. Yeah, so that was pretty cool. All right. Just back to here. All right. So one of the pages I gave you guys last week had to do with these Doppler shifts. This bunch here. So I'm not going to pick up this page, and but yeah, I did want to go over a few of these with you guys. Get some extra practice with the Doppler shift. Think about how this works. Okay? So start with these. There are different scenarios. Starts off real basic, and then at the end, last one has a fun twist to it. But let's start with the real basic one. So scenario one. Okay. I've got a car traveling at 25 meters per second. You guys see right there, going left to right. Okay. Let's use speed of sound as 343 meters per second. And maybe this car horn has a frequency, and maybe the dominant frequency is 440 hertz. So like beep beep, could sound like an A note, right? Let's have these two people are just standing there, just standing out, maybe on the sidewalk. Right? What frequency does, well, we've got 3 different perspectives. So first perspective is inside the car. Because if you're traveling along with the car, with the pocket of air that's traveling with the car, do you think you also hear 440 hertz? Yeah, so that's the first box is just whatever the car horn frequency is. And I do have different versions of this, so I don't know if your guys' paper has the same numbers, but whatever that number is, okay, goes here. All right, then person A versus person B. Should person A hear a high pitch or low pitch? Yeah, should be low. So the number should be less than 440 hertz. Okay? Bring this out to projector and then do a practice run with you guys on this. Right, so maybe I could say that, you guys remember Doppler shift, the observed frequency is equal to the source frequency. You know what? I should have gone landscape with this. Okay. The observed frequency is equal to the source frequency. Okay. Now, if everybody's just standing around, if nobody's in motion, isn't that the entire story? Everybody agrees on what the frequency is. Okay. But if somebody's in motion, then you have to multiply by this ratio. Go on speed of sound plus or minus the observer speed divided by speed of sound plus or minus the source speed. Right? In this case, the car is providing the source of the sound, right? The car horn, like that, right? Now this would all be in one dimension. So like if you're staying out by the sidewalk, it's approximately the road, right? Something like that. Okay. So let's start with the 440 hertz. Okay. And then multiply by, now this would be frequency observed by person A. So observed by person A. So she's 343 meters per second for the speed of sound. Plus or minus here. Okay. Now, since person A was just standing there, then what's that person's speed? Yeah, 0. That just goes there. Okay, so the numerator is easy to work with. Okay. But the car is in motion. The car was going at 25 meters per second. Okay. Now here's where I got to figure out plus or minus. And different textbooks will explain different ways, when to apply a plus or minus. Some textbooks say define it having to do with the direction of motion. I like to reason it out for each individual case, what's going on, case by case basis. So the fact that the car is going away from person A, should that lead you to adding or subtracting down here? You're right, it is adding for person A. Okay. Now, well, why would that be? Well, because that would make the denominator bigger, right? Which makes this overall fraction less than 1, right? Maybe like 0.9 something, which means you take this original 440 hertz, multiply by something less than 1, you'll get a pitch that's smaller than 440 hertz. That's the end goal. You do know, you guys did tell me even before I wrote anything, that this observed frequency has to be less than 440 hertz. Okay? So yeah, and the only way to get there is to add on the bottom. Try this out. 440 times 343 over 343 plus 25. Okay? That's telling me 410 hertz. Yeah, I can believe that. That looks about right. 410 hertz. Okay. So for person B, wouldn't the only difference be the car is headed towards the person? So should I just swap out the plus with the minus? Okay. And that's it. So I'll go 440 hertz times 343 meters per second over 343 minus 25 meters per second. Yeah. And then the calculator, I'll have to scroll up, scroll over, and pop in a minus sign. Okay, and I'm looking at 475 hertz. That number looks about right. It's more than 440. It should have been. Okay. You guys good there? It's a real fundamental example there. Yeah, what's that?
So I have my rubber bands and I'm playing with them.
Oh
When
yeah?
I make it really tight and long, it's a high frequency and it's high pitch.
Yeah.
And then when I make it shorter, it's a lower frequency, lower pitch. Why
Yeah.
is that? What does the length have to do with the frequency?
See, it's not just the length; it's also the tension in it too. Let me find. See, where is it? Chapter 14. Sound. Let's find the equation that we're going to care about here. oh, there's we got stuff like decibels and stuff that we're looking at here. Doppler effect. I just had this morning too, didn't I?
Tension is directly proportional to the velocity. Tension.
Hold on, where'd it go? Oh, oops, I skipped over it. Ah, here it is. All right, so back to these strings. All right, so yeah, the frequency, whoops. Gotta switch my screen here. Okay. So the, you said when you pull that band tight, it's like a higher frequency, right? Something like that. Right. So yeah, so the frequency has to do with not only the length of the band, but also, hey, look at this. We got the square root of, we got a tension here. That's what this F is, right? For force, like tension force, right? Yeah. So when you pull on that band, it increases the tension. And that's probably like the main driver of for the frequency, right? There's also an effect for how long it is, right? That's what that L is. Okay? Oh, and you know what else would change? Actually, this linear mass density would change a little bit too, wouldn't it? Because if you pull it, then that same mass is now stretched over a little bit longer distance. So yeah, so looks like a bunch of these variables change. Yeah, so that could determine what the ultimate frequency is going to be. All right, go back to these. Okay, so there's different scenarios. What's going on? Since we only got a couple minutes left, let's look at this very last scenario. This very last scenario, we're throwing rocket boosters on the car, and the car is going 600 meters per second. Okay? Now, let's start with person E. Car's traveling away from person E. Does person E hear a very high or a very low pitch? Very, very low, right? Regular Doppler equation, all that, right? What about person G, who the car is sort of headed towards? What is this person here? Wait a minute. This might be a, tell you what, if you ran the Doppler equation, you would actually end up with a negative number. Wait, what are you saying, Eric? Wouldn't hear anything at all. Why would you not hear anything at all? Ah, yeah, this is actually a trick question here at the end. Yeah, you guys got it. This car's traveling faster than the speed of sound. Yeah, person G doesn't hear anything until the car reaches him, but the car is going to reach him first, right? This car is outpacing the very sound waves that it's sending out into the atmosphere. Yeah, so good catch there if you got that. All right, so anyway, you guys got these for extra practice problems. Like I said, I'm not going to pick up this page though. Right? Anybody got any questions from today? All right, so before you walk out the door today, if you haven't turned in your chapter 13 yet, then pop those in the gray tray. Also, your speed of sound lab. So turn that in before you walk out the door, your speed of sound lab. And then you guys online, of course, upload that to Focus. You guys remember you have a take-home quiz, and I'm going to pick that up Friday. Unless, of course, you want to turn it in early. You can always turn it in early. But you guys got a 10-question take-home quiz.
It's not like the force of it taking off.